Section: Introduction. In this section, we discuss the advancements in language models, particularly focusing on transformers and state space models, SSMs. While transformers excel in performance and memory recall, they face challenges due to their high computational costs and memory requirements. On the other hand, SSMs like Mamba and Mamba 2 offer constant complexity and better hardware efficiency but struggle with memory recall, impacting their overall performance. We introduce our new architecture, Hymba, which combines attention heads and SSM heads within the same layer. This hybrid head design allows us to process inputs in parallel, leveraging the strengths of both approaches. By doing so, we enhance the model's ability to manage different types of information and memory access patterns. To further boost Hymba's performance, we add learnable metatokens to the input sequences. These tokens act as a compressed representation of knowledge and help improve attention mechanisms, especially in tasks requiring memory recall. We also propose sharing the key value cache between layers, inspired by the correlation observed in consecutive layers. Additionally, we utilize sliding window attention in most layers to reduce cache costs. Our evaluations show that Hymba achieves state-of-the-art performance across various tasks while being more efficient than traditional transformers and previous hybrid models. For example, in common sense reasoning tasks, our model, Hymba 1.5b, outperforms LLaMA 3.2 to 3b with higher accuracy while requiring significantly less cache size and being faster. We optimize Hymba for on-device tasks through supervised fine-tuning, resulting in our instruction-tuned model, Hymba 1.5b Instruct, achieving top performance on several benchmarks. We also outline a roadmap for developing efficient small language models, emphasizing the benefits of fusing attention and SSM heads in parallel, which enhances reasoning and recall accuracy. Our approach includes optimizing the hybrid head module for efficiency and cache sharing, leading to improved throughput and reduced cache requirements. Lastly, we introduce metatokens that enhance focus on relevant information and encapsulate world knowledge, further boosting our model's capabilities. Section Summary. In this section, we introduce Hymba, a novel language model architecture that combines attention heads and state space model heads within the same layer to enhance processing efficiency and memory recall. We also discuss the implementation of learnable metatokens and optimized KV cache sharing, which together improve performance and efficiency, establishing new state-of-the-art results across various tasks. Section: A fused hybrid head module. In this section, we introduce a fused hybrid head module. While SSM models are efficient, they struggle with recall and task performance, as shown in our results. Our goal is twofold. First, to merge the efficiency and context summarization of SSMs with the high recall capabilities of attention. And second, to create a fused building block that can be a key component for future foundation models. Previous hybrid models typically combine attention and SSMs sequentially, which can create information bottlenecks when a layer is not well suited for a specific task. Inspired by the multi-head attention structure in the transformer, where different heads focus on various contexts, we propose a new method, integrating attention and SSMs in parallel within a hybrid head module. This design allows different heads to handle the same information in unique ways, leveraging the strengths of both approaches. We represent the hybrid head module with a unified and symmetric formulation. Given the input sequence, which includes original data and additional metatokens, we project this input to create queries, keys, and values for the attention heads, as well as input features and gates for the SSM heads. The output from the attention heads is calculated using a softmax function applied to the product of queries and keys, while the SSM heads utilize a data-controlled linear operator. We notice that the outputs from the SSM heads are generally larger than those from the attention heads. To ensure effective integration, we normalize and rescale these outputs using learnable vectors, then average them before a final output projection. The overall formulation of our fused module is symmetric, with learnable vectors adjusting the outputs from both head types. From a memory perspective, we can liken the components of our hybrid head module to functions of the human brain. The attention heads act like snapshot memories, providing high recall resolution, while the SSM heads serve as fading memories, summarizing context over time. Our approach allows for more snapshot memories to be allocated for local information while maintaining recall capabilities by prioritizing local attention over global attention. We also analyze the importance of attention and SSM heads in each layer by setting the learnable vectors to 0 and measuring the impact on accuracy. Our findings indicate that the importance of each head type varies based on the input and task. Notably, the SSM head in the first layer is crucial for language modeling, and its removal significantly reduces accuracy. Overall, removing one head type typically results in a small drop in accuracy, highlighting the complementary roles of attention and SSM heads. Section Summary. In this section, we propose a fused hybrid head module that combines the efficiency of SSM models with the high recall capabilities of attention mechanisms by fusing them in parallel, allowing different heads to process the same information in unique ways. We also analyze the importance of each head type, finding that their roles are input adaptive and critical for task performance, particularly highlighting the necessity of SSM heads in language modeling. Section: KV Cache Optimization. In this section, we discuss our approach to optimizing the KV cache. Our hybrid head module enhances recall and reasoning but can reduce memory and throughput efficiency due to the KV cache needed for attention heads. To tackle this, we aim to minimize the KV cache while keeping task performance similar. We combine global and local attention. Local attention, or sliding window attention, SWA, is more efficient than global full attention but may lose some global context. However, since our hybrid head module includes SSM heads that summarize global context, we can replace global attention with local attention more effectively, achieving a better efficiency performance balance. We explore the ratio of local to global attention. Initially, we replaced global attention with SWA in all layers, which significantly hurt recall, dropping accuracy by over 20% on recall-heavy tasks. To remedy this, we gradually reintroduced global attention in some layers. We found that using global attention in just the first, middle, and last layers was enough to restore recall accuracy while keeping common-sense reasoning accuracy stable. This approach led to a 2.7 times increase in throughput and a 3.8 times reduction in cache usage. Next, we implemented cross-layer KV sharing. We noticed that the KV cache is quite similar between adjacent layers, so using separate caches for each layer creates unnecessary redundancy. By sharing keys and values between consecutive layers, we reduced both KV memory usage and model parameters, allowing us to reallocate saved parameters elsewhere. This strategy improved throughput by 1.15 times while maintaining recall accuracy and increasing common sense accuracy by 0.60%. We also introduced meta tokens. We observed that initial tokens, while not semantically important, often received high attention scores from later tokens. To address this, we created learnable meta tokens to serve as initial tokens. These meta tokens are added to the input sequence, allowing the model to focus more on meaningful tokens during task performance. At inference, since the meta tokens are fixed, their computation can be done offline, acting as a learned cache initialization to guide attention. From a memory perspective, meta tokens help in the attention and SSM calculations of subsequent tokens, similar to how metamemory functions in the human brain. We visualized the attention scores for meta tokens and found that different tokens activate for prompts from various domains, indicating that they encapsulate different knowledge that can guide attention. We hypothesize that meta tokens serve several functions. They prevent token overriding, as attention can sometimes overly focus on certain tokens. By adding learnable tokens, we create more representative feature maps. Additionally, meta tokens help manage the forced to attend issue by modifying the softmax function's shape, allowing for better attention distribution. Finally, We see meta tokens as a form of learned initialization for the KV cache and SSM state. While we use one set of meta tokens for all tasks, they enhance recall and common sense reasoning accuracy. Our analysis of the attention map's entropy before and after introducing meta tokens shows a reduction in entropy, indicating that both attention and SSM heads focus more on important tokens, thus improving task performance. Section Summary. In this section, we optimize the KV cache in our hybrid head module by combining global and local attention, finding that using local attention with selective global attention layers significantly enhances efficiency while maintaining recall accuracy. We also introduce learnable meta tokens to guide attention towards meaningful tokens, which improves recall and common sense reasoning capabilities, as evidenced by reduced attention map entropy and enhanced task performance. Section: Hymba Attention Map. In this section, we discuss the Hymba attention map. We can see Hymba's attention pattern as a mix of components from sliding window attention, meta tokens, and SSM. We categorize the elements in the attention map into 4 types. 1. Meta. This includes attention scores from all real tokens to meta tokens, showing the model's preference for these tokens. They typically appear in the first few columns of the attention map. 2. Boss. These are attention scores from all real tokens to the beginning of sequence token, usually found in the first column after the meta tokens. 3. Self. This represents attention scores from real tokens to themselves, generally located along the diagonal of the map. 4. Cross. These scores are from real tokens to other real tokens, appearing in the off-diagonal areas. We visualize the attention maps from LLAMA 3.2 to 3b and HYMBA 1.5b using texts from Chapter 29 of Oliver Twist, summing the attention scores from different categories and normalizing them by context length. For SSM heads, we follow previous methods to calculate and normalize their attention maps. We notice that Hymba's attention pattern differs significantly from traditional transformers, which tend to focus more on the boss token and have a higher proportion of self-attention scores. In contrast, Hymba's design allows meta tokens, attention heads, and SSM heads to work together, leading to a more balanced attention distribution. Specifically, meta tokens reduce the focus on boss, enabling more attention on real tokens. SSM heads summarize the global context, emphasizing current tokens, while attention heads focus less on self and boss tokens and more on cross tokens. This hybrid head design in Hymba helps balance attention across different token types, potentially enhancing performance. Next, we introduce the Hymba model family, which includes models of sizes 125M, 350M, and 1.5B. We train these models using a combination of datasets, including DC-LMBASELINE 1.0 and SMOLM corpus, with varying token counts. We implement a learning rate scheduler and data annealing techniques to ensure stable pre-training, using a sequence length of 2,000 tokens and a batch size of 2 million tokens, increasing the sequence length to 8,000 tokens for the last 100 billion tokens. For model evaluations, we establish our baselines with popular small language models that use quadratic attention, as well as hybrid models. We adopt 2 benchmarking settings, one where we directly compare our Hymba models against state-of-the-art small language models, and another where we train different architectures from scratch under the same conditions. We evaluate our models on common sense reasoning and recall-intensive tasks, as well as on downstream tasks like math and role-playing. In our benchmarks, we present results for our Hymba models of sizes 125M, 350M, and 1.5B, comparing them to other small language models. Our HYMBA 1.5B model, trained on 1.5 trillion tokens, achieves the best performance among sub-2B models, showing improved throughput and cache efficiency, especially with longer sequences. For example, compared to the strongest sub-2B baseline, SMOL LM2 to 1.7B, our model shows a notable accuracy improvement and significant reductions in cache size and increased throughput. We also find that our smaller models, Hymba 125M and Hymba 350M consistently outperform other models of similar sizes. Additionally, we provide a version of the Hymba 1.5B model trained solely on public data. Section Summary. In this section, we describe the Hymba attention map, which integrates components from various attention mechanisms and categorizes attention scores into 4 types: meta, boss, self, and cross, revealing a more balanced attention distribution compared to vanilla transformers. We also introduce the Hymba model family, detailing our training process and benchmarks, where our 1.5B model outperforms other small language models in accuracy, cache efficiency, and throughput, despite being trained on fewer tokens. Section: Benchmark different architectures under the same setting. In this section, we benchmark different architectures under the same conditions to compare their performance on general and recall-intensive tasks. We conduct a thorough comparison between our Hymba model and other architectures, including the standard transformer, Llama 3, pure Mamba, Mamba with feed-forward networks, and a hybrid model called Samba. All models have the same number of layers and parameters to ensure a fair comparison. We train them on identical data with the same hyperparameters and codebase. To validate our findings, we perform experiments at different scales, 1 billion and 300 million parameters, and with different datasets. We evaluate the models on tasks such as language modeling, recall-intensive tasks, common sense reasoning, and question answering. Our results show that Hymba consistently outperforms other 1 billion parameter models, achieving an average score that is 1.45% higher than the second-best model at the 300 million scale and 1.74% higher at the 1 billion scale. We also examine the performance of Mamba models on real-world recall tasks, where they struggle due to their limited recall capabilities. In these tasks, Hymba, which enhances Mamba with attention heads, performs better than both the transformer and Samba architectures. Next, we conduct a direct comparison of Hymba, Mamba 2, and Llama 3 on a synthetic retrieval task called Needle in the Haystack. In this task, a random sentence is embedded in a long document, and the model must retrieve it. All models are of the same size and trained under the same conditions. Our findings indicate that Hymba significantly outperforms both Mamba 2 and Llama 3. While Mamba 2 shows good performance when the needle is at the end of the document, it struggles when the needle is at the beginning or middle. Llama 3 also has limitations in retrieving the needle from the middle of the document. We then discuss the implementation details of our instruction-tuned model, Hymba 1.5B. We use a 2-stage post-training strategy, including full fine-tuning and direct preference optimization, with specific learning rates for each stage. We compare Hymba 1.5B instruct with other lightweight instruction-tuned models across various tasks. Our evaluation results show that Hymba 1.5B instruct achieves the highest average performance, surpassing the previous state-of-the-art model by about 2%. Additionally, we explore the compatibility of Hymba with Dora, a parameter-efficient fine-tuning method. This approach is beneficial for on-device scenarios with limited resources, as it requires storing only a small fraction of the original model's parameters. We fine-tune Hymba on Rollbench using Dora to improve its role-playing abilities. Our results demonstrate that Hymba Dora outperforms larger models in instruction and role generalization tasks, indicating the effectiveness of our approach in enhancing model performance. Section Summary. In this section, we conduct a comprehensive comparison of our Hymba model against various architectures, including Llama 3 and Mamba, across multiple tasks, demonstrating that Hymba consistently outperforms these models, particularly in recall-intensive scenarios. Additionally, we explore the effectiveness of instruction tuning and parameter-efficient fine-tuning methods, showing that Hymba achieves superior performance in role-playing tasks while maintaining a smaller parameter footprint. Section: Related Works. In this section, we discuss related works in the field of large language models, LLMs. Before LLMs became prominent, Transformer-based models effectively captured relationships between tokens in complex sequences using an attention mechanism. These models also scaled well in terms of size and the amount of pre-training data, leading to the development of LLMs like GLM, Opt, Mistral, the Llama series, Gemma, and GPT-4, which excel in zero-shot and few-shot learning. However, despite their advantages, transformer-based language models face challenges due to the quadratic computational complexity and the increasing size of the key-value cache in attention modules as sequence lengths grow. To tackle this, efficient language models with subquadratic complexity and strong scaling properties have been developed. Notably, models like RWKV and RetNet are seen as variations of state space models, SSMs, using a linear dynamical system approach with fixed-size memory to encode past information, allowing for linear scaling with sequence length. Hymba, a widely used SSM, enhances previous models by selectively managing information along the sequence, outperforming transformers in various tasks and providing faster inference. Subsequent models like Hymba 2 and GLA have introduced more efficient gating mechanisms to improve training speed, but SSMs still struggle with recall and in-context learning tasks. To merge the efficiency of SSMs with the recall strengths of transformers, we see a trend toward hybrid models. For instance, Hymba Former combines Hymba and attention modules to boost in-context learning. Research shows that adding a few attention layers to a Hymba model can significantly improve common-sense reasoning and long-context capabilities. Models like Jamba and Zamba have developed stacked Hymba attention hybrids, with Jamba incorporating mixture of experts in the MLP layers and Zamba using a shared attention module, both achieving better inference speed and accuracy than earlier transformer models of similar size. Samba introduces a structure that stacks Hymba, SWA, and MLP layers in a repeating pattern, maintaining constant throughput as sequence lengths increase. Other recent studies have also explored hybrid models that combine linear RNNs or convolutions with attention, proposing a new model with a fused multi-head building block that stacks hybrid operators in parallel. Our model shows superior performance compared to previous architectures, as demonstrated by extensive benchmarking.